Hello everyone, myself Ketan Bhavsar, Assistant Professor in LJ Engineering College, Ahmedabad. In VLSID Design Unit number 3 MOS transistor. Today's topic we are talking about thresholding. As you all know, this particular word is very popular in each and every field when we are talking about the thresholding, because this word we are hearing from more than last 2 to 3 years. Because what exactly the meaning of threshold, that you have to provide the sufficient amount of voltages to trigger any specific hardware or gadgets. Now we go into the depth. In previous session we discussed about what is MOS transistor, MOS structure, what exactly the terminal of gate, drain and source, and also we discuss about the body terminal and how that particular terminal will affect when we apply certain voltages. Also we study external bias voltage when you apply a gate to source and drain to source voltage on particular terminal, and what exactly the effect will produce inside the system. And also we study about different types of voltage variations and also its region like accumulation, depletion, surface inversion. And after that surface inversion we are also talking about a linear cutoff and saturation region in terms of a pinch or point of view. So in previous session we discussed about the Mosfet structure, its external bias voltages, and also its characteristic in terms of when you apply the external voltages. And we see when device is generally form the linear variation, when channel will be establishment, and when channel will be formed from source to destination, and when it will become break when you increasing more and more BDS and it became BDS saturation, then channel will be cut off, or we can say that the channel will be break from the source region. So now in today's topic we are discuss about thresholding. So in first case, what is thresholding? So in the first case we are considering the VGS is equal to 0 and drain, source and bulk are connected to a ground. The drain and source are connected by back-to-back PN junction, means substrate source and substrate drain terminal. Under the mentioned condition, both the junction have a 0 voltage bias and can be considered as a off, which result in extremely high resistance between drain and source will be created because there is no external voltage is applied. So as you can see, the results is look like this. So when you apply the certain voltages, so it's you can see the variation is look like this, like a drain terminal, source terminal, gate terminal and body terminal, and also the depletion region will be formed in this region. So we can easily identify that how we can connect the data and how we can monitor and observe the variations when channel will be formed. So now we go into the depth. There are the main 4 components when we talking about the thresholding and threshold voltages. So first, the work function difference between gate and channel is a 5GC. The gate voltage component to change surface potential is minus 25F. Gate voltage component to offset a depletion charge minus QBO upon COX. And also offset field charge in gate and oxide minus QX upon COX. So these are the main 4 components when we talking about the thresholding and how thresholding is actually affect a specific transistor level. Now work function defined is denoted by phi. So now let's consider the first condition. So now take the first condition is 5GC between the gate and channel. So as we can see, as per our energy band diagram, we consider the substrate. So 5GC is equal to 5F minus 5M, M for the metal and F is considered as a substrate. So as we consider 5F, 5M and now 5F substrate minus 5F substrate. So now we consider 5GC is equal to 5S minus 5F. So we consider it's a substrate. Now we consider as a substrate. If VGS is greater than VTO, So now the channel will be start forming. So near the surface, the negative charge will be produced. So 5s is equal to minus 5f. And now the work function difference, if we put in this particular equation, as you can see, the 5s is equal to minus 5f. So we get total 5gc is equal to minus 25f. The gate voltage required for surface inversion is minus 25f. The reason is very clear, because first of all, the holes near the surface, after the surface inversion, it create a electrons layer. So because of that reason, the potential difference is negative. So minus 25f. Another component of the applied gate voltage is necessary to offset the depletion region charge, which is due to the fixed acceptor ions located in depletion region near the surface. So now we consider about the near the surface. So depletion charge, we consider VSB is equal to 0. So QB is equal to minus 2QNA epsilon SI minus 2 phi F plus VSB. So in this situation, as you can see, we have a two scenario. VSB is equal to 0 means we are considering the substrate bias is 0 and substrate bias is not equal to 0. So QBO for the oxide is equal to minus 2 phi 2 Q for the charge, NF for the number of acceptors, epsilon SI for the permittivity of free space, and minus 2 phi F as we are getting from the surface inversion, because 5gc is equal to minus 2 phi F. And now in this situation, we consider the VSB is equal to 0, but now we can see if it is not equal to 0, then we have to add the VSB in this particular equation. So as you can see, we have to add in this particular equation term. And we also consider the two value here, because we are always considering in for the PMOS and for the NMOS. So as we have already equation C is equal to epsilon A divided by D, its area divided by D, V is equal to Q by C. So now after the semiconductor and for the oxide region, V is equal to minus QBO upon COX, because right now we are considering the Q is equal to QBO and C is equal to COX, where COX is equal to the capacitance between oxide and gate terminal. So V is equal to minus QBO upon COX for this particular region. Now after that, the component that we have, it's for a particular fixed gate at charge oxide, or for the oxide capacitance, it's minus QX upon COX. And similarly, we have a depletion region for minus QBO upon COX. So this two component, it's still remaining, that how the component in terms of the depletion region and also in terms of the charge, it will affect on the terminal. So as you can see, so the total voltage at VSB is equal to 0. So we are considering right now VTO is equal to 5GC, means we are considering gate to source or 5GC terminal, minus 2 phi F that we have, means surface inversion. Now QBO upon COX that we have, it represents specifically for the body terminal and for the substrate, and for the charge minus QX upon COX. So in this situation, these four parameters are actually affect a specific threshold voltages, as we see in first case. And similarly, if you're talking about a threshold voltage, then we have considered it's a VT consider here that 5GC minus 2 phi F, or here we are considering VBO is equal to QB, means QBO instead of QBCOX minus QOX upon COX. Right now we are considering VSB is not equal to 0 as per this equation, as you can see like this. We are considering here QBO and we are considering here QB, that if VSB is not equal to 0. Fine. So now as you can see, now we put a generalized equation. We have to calculate the total threshold voltage VT. So for calculating the total threshold voltage VT, we are considering the VT is equal to 5GC minus 2 phi F minus QBO upon COX minus QB minus QBO upon COX, because right now we are talking about both the situation when VSB is not equal to 0 and VSB is equal to 0. So QB minus QBO upon COX minus QX upon COX. So we ideally consider here that we cancel out these equations. We are getting QB upon COX. So it's a generalized term that we already see in previous slide. Now you can see the 5GC minus 2phi f minus QB upon COX minus QX upon COX minus QB minus QB upon COX. So now VT is equal to VTO minus QB upon CX, because we have the equation. This equation is similar to this one, as you can see. So we put directly VTO over here. So we can see the QB minus QB upon COX is equal to, now we are put at the equation of VTO that we are seen in first slides, like this one. QB minus QA minus 2QNA epsilon SI in mode minus 2phi f plus VSB. As you can see, if VSB is not equal to 0 and VSB is equal to 0. So as you can see, we just try to simplify the equation, nothing else. And here is also minus 2phi f. We are not consider a VSB over here. So now we put the equation QB minus QBO upon COX is equal to minus 2QN epsilon SI in bracket in mode minus 2phi f plus VSB minus mode of 2phi f, because we put a common terms 2QN epsilon from this equation. So VT is equal to VTO minus 2QN epsilon SI by COX in bracket, we are discussing minus 2phi f plus VSB minus mode of 2phi f and bracket close. So now as you can see, we have equation VT is equal to VTO plus gamma, we are considering as a coefficient, and in bracket in under root of minus 2phi f plus VSB mode completed minus mode of 2phi f. So in this situation, we are taking care of threshold voltage in both the situation. If VSB is not equal to 0 and VSB is equal to 0, because ideally we have to take care of these two conditions, because if these two conditions will fulfill, then and only then we can work on other conditions, and then and only then we move on other possibilities. Now we take a coefficient, it's gamma, as you can see. So gamma is equal to 2QN A epsilon upon COX, a substrate bias coefficient. So you can also call it as a substrate bias coefficient gamma, because in exam they are asking this question in multiple way, like prove the gamma coefficients, prove a substrate bias coefficient, prove the threshold voltage. So in this all the question you have to write down this particular equation for VT. So I hope that you getting the idea about what exactly the threshold voltage is and what exactly the importance of threshold voltage when we are dealing with a specific linear cutoff and saturation region, and how it will affect on particular domain. So in next session we are talking about the current and voltage characteristics, and we are dealing with a VDS and VGS, VT and ID equations in next session. And then that particular situation we are talking about different types of Mosfet characteristics when you increase a voltage level and the channel will be formed from drain to source terminal, and how the channel width will be decreases if you increase more and more VDS, and what exactly the situation and the scenario will be produced for the current. So I hope that you really like this session, and if you have any doubt related to this particular topic and this particular method, then we definitely talk about the next slide, and also make sure that this characteristic is play a main role when you are dealing with any electronics or any component which affect a specific methods or which affect a specific threshold voltage limits. So I hope that you like this session, and make sure that this particular diagram you can see in each and every datasheet modules. If you're talking about the transistor, MOSFET, if you're talking about any chip like AND gate, OR gate, any microprocessor, microcontroller, you can definitely get the equation of ID, VDS and VGS. So I hope that you like this session, and thank you very much.